Hello everyone. I'm sorry I did not was unable to do it Thursday, but we will get through the first class now, and I'm recording this, so please watch the recording before our next class at on Wednesday 7 a.m. Okay, so here very quickly we will go over our syllabus. And in this course, we will be dealing with some of the topics that we don't usually go over in the undergraduate reinforced concrete design. Um, so the textbook that we will be following is Design of Concrete Structures by Darwin, Nolan, and Nilsson. That is the book. And I will upload the PDF of the book in the on to eLearn, so that should be available soon. Sorry. Okay. The codes that you need mainly is ACI 318 2019 and ASC 710. Both of those I will be putting the PDF. So here is the 2019 ACI 318, but you may note that in some companies they may still be following the ACI 2014. 318 2014. So if sometimes we will go over that as well. Software, mainly we will be using the structure point software, SPBeam, SPcolumn, etc. I also have some Excel sheets that I will provide, and we will use those as well. So here is the course content. So we will first go over serviceability in a bit more detail than we do in the undergraduate class. So today I think I will cover except shrinkage and temperature deflections. I will try to cover everything else. Next, we will go to continuous beams and one-way slabs, that is indeterminate systems. So we will, if those of you who took advanced steel design already, you know how to use, how to do plastic analysis, and that way you get the full capacity of the structure and you can design a more economical member. So the same thing in reinforced concrete structure, you can use some moment redistribution to reduce the amount of steel that you need. So for this, we will be using, a lot of times we will be using the design examples from Portland Cement Association, PCA. They are some of the, or they are one of the go-to places for concrete design, and several of the codes in ACI 318 are based on the research to which they have contributed a lot. Then we will go over part of pre-stressed concrete design, pre-stressed flexural members, partial pre-stressing, and so on, anchorage. Then we will go over two-way slabs. So as you know, or as you might remember, in ACI 318 2019, direct design method is no longer there. But like I said, it is a older method and we can still use it. It is, it is given this way. If the ACI 318 code says that neither direct design method nor equivalent frame method are specifically outlined in the code, but the designer is free to use a textbook to use either of these methods. That is what is specified in the code. So we will be learning both of these methods, direct design and equivalent frame method both. For equivalent frame method, we will use the SPBeam software. Okay. Then we will go over design of slender columns, and finally some part of seismic design, okay, using the response spectra and so on. Okay, so homework mostly it may consist of part of it may be by hand calculations and part of it may be using software. So since the course is online, everything is on eLearn. Please do your homework and submit it online. We won't, we will have midterm exam, but it will be only one midterm exam by online. So you will do it yourself and upload the solution online. And the rest, not much more. We can get started with serviceability. So for each topic, we will be doing a bit of overview so that whatever you may have covered in a regular undergraduate reinforced concrete design, you can recall. Okay. So we are starting with serviceability. So as we know, the design of a structure must account for 3 S's: strength, serviceability, and stability. And the next one is economy. So what is the purpose of stability in reinforced concrete design? So you want to limit excessive deflection, cracking, vibration under service loads, okay? Then for this is as far as bridges, floor slabs, any of these, you don't want excess deflection. Supposing, let's say you have sensitive machinery, which is the most simple case is it has to be level for it to work properly. So if your deflection is excessive, then over time the level will change with, for example, with long-term deflection or with an application of new load. So then your machinery may not work properly. Cracking is generally you want to restrict or in any case we want to restrict the cracking only to hairline cracks, because this will ensure that the reinforcing steel is not getting corroded. Hairline cracks, generally accepted limit is 0.016 inches. Okay, so but now we in regular reinforced concrete, in order for the steel to be useful, we must have cracking. So we cannot avoid cracking unless we are going for pre-stressed concrete. So we do need the cracking in order for this tension to develop in the steel, but we want to limit those to hairline cracks. Okay. So some very general points about cracking. So if you use very few rebars but large cross-sectional area, then you will have only a few cracks in your beam, but they will all be large. We don't want that. If instead you use many rebars of a smaller cross-sectional area, then you will have smaller hairline cracks, but many of them along the length of the beam. That's what you want. Okay, directly we went to beam because deflections are far more important for beams than for columns, which are usually under tension, compression. Okay, so the next concept, the next aspect is for durability. As you know, as we just mentioned, the crack widths are crucial to prevent the corrosion of steel, and therefore they ensure the durability of the structure. Impermeability. So sometimes when your structure is holding something, let's say hazardous material, then you do not want any cracking at all. So then you may need to go for pre-stressed concrete, or you want to maintain certain level of permeability, right? and then acoustic and thermal insulation. Those will determine your concrete cover, and concrete cover will in turn influence the cracking. In general, if you have a larger cover, the crack will also be larger. You can imagine. So when the crack needs to go up to the level of the rebar, so when it starts, as it propagates, it will get progressively larger at the end of the cover. Okay, so as you know, we will only study LRFD, although you may know that the earlier method of design was ASD, or allowable stress. So from regular reinforced concrete, you may remember that the allowable stress design, in allowable stress design, all the both concrete and steel were behaving in the linear elastic regime. So I will just so if you look at steel, so that is the stress strain curve for mild steel. And that is the stress strain curve for concrete. Okay, and here is your value FC prime, and this is obtained from the cylinder compression test, and this is epsilon u, which we usually take as 0.003. Okay, now here this yield point is 0.2%. Just a second. 0.002, yeah, so 0.2%. It starts to yield, and the hardening starts at 1%. Okay. Okay, approximate value. Let me check the approximate value. Yes, that's right. It is at 1%. Okay. So in what was being done in allowable stress design was that both concrete and steel, the stresses in both concrete and steel were kept to within a certain value in the linear elastic range. So in allowable stress design, serviceability was not explicitly accounted for, because it was anyway in the linear elastic range, the deflections are very small. But when we go to LRFT, we are using the steel is yielding, we must have yielding, and we also let the concrete reach its maximum compression value under ultimate loading. But since the steel is yielding, you are getting cracking in the tension region, and that will automatically increase your deflection. So therefore, in LRFT, you must explicitly account for serviceability. Okay, so there are on a very basic viewpoint, there are two methods to ensure serviceability. So if you want to ensure serviceability, there are two methods. One is you restrict or you provide a minimum member thickness, okay, or you explicitly calculate the deflections. So this is serviceability as it relates to deflections. So if you are not meeting the minimum member thickness, then you must calculate the deflections and ensure that they are within code limits. Okay. So let me just explain that. Let's say that we are we are taking care of stability by providing minimum member thickness. Then what you will do, let's say we are designing beams. So here in chapter 9, which is for beams of ACI 318, it is specified your depending on the end conditions, your minimum thickness of the or minimum depth of the beam, total depth H, not D, is specified, right? So if you choose your beam depth according to this, then even if you don't explicitly calculate deflections, you're okay. Okay, but okay, same thing you also have for one-way slabs. Let me go to that page. Okay, let me reopen it. Okay, so if you're dealing with one-way slabs, then you would go and look at your minimum thickness for one-way slab. So that's one way to take care of stability. Or you need to explicitly come and calculate the deflection. So that is in your serviceability chapter, and we will be going through that now. Although some of it you have covered in the undergraduate course, we will be going over a bit, quite a bit beyond that. Okay. Okay. So what, from where do you get deflections in flexural members? So shrinkage, temperature, short-term deflections, that is elastic deflections, and long-term creep. Usually in the code, the shrinkage and temperature are included within the creep calculations, but we will also learn how to do it explicitly. Okay. Okay, this I've briefly explained already. Now, okay, so I've spoken about this. So the way you want is, so this is the pattern. So that's the pattern for this beam. You can see that this beam had very few rebars, but large cross-section rebars, larger rebars. So this beam will have wide cracks, but not many. And if you look at the beam which has many smaller cross-section rebars, then it will have many hairline cracks. They are not wide, but they are numerous all along the length of the beam. That is what we prefer. We want the cracks to be within 0.016 inches. Okay, so the analysis of we cannot do exact analysis to calculate crack widths. It is quite a complex process because you can see that once cracks open in along one section, then it will immediately start somewhere else. So it is a dynamic process of crack opening, and we do not want to go for a theoretical calculation for crack opening process. Instead, we use the empirical relationships based on experimental data. Okay, let me. There is some problem with the picture. Let me restart the PowerPoint. Oh, okay, just a second. Okay, there we go. Now, crack width is based on, as I said, bar spacing and clear cover. Okay, so when you provide a larger clear cover, then your crack widths will increase. Okay, and when you have more bar spacing, your crack width will again increase. So these are two different equations. One of them is by Gergery and Lutz, the first one that you see. The second one is by, just give me a second, Frosch. So the second one is by, and this is by Gergery and Lutz. So what you see here is W is the crack width, and this beta is a ratio. Let me write here what is beta. The beta that you see here is a ratio of H2 by H1. What is H2? H2 is the distance from the bottom to the neutral axis. H1 is the distance from the center of the rebar layer to the neutral axis. So that is beta. Okay. So Fs is the stress developed in the steel under service load. So for Fs, if you're not doing an exact calculation, you can assume Fs is 2/3 of Fy. Okay, you can assume that under service loads, the stress in the steel is 2/3 of the yield stress. Okay, now uh, A is the concrete area which is surrounding one bar. So for example, if you're dealing with this bar, then you will take, we will see how to calculate this area. This is the area surrounding one bar. and DC is the thickness of the cover, um, measured from here to the center of the bar. Okay, so DC is, so if you have a bar, then DC is measured from the tension face to the center of the bar. Okay, that is DC. All right. So this is for Gergery Lutz, and in Frosch, S is the spacing of the rebars. So you can see that okay, beta is so you can see in both cases that okay, this is equation 7.1. It goes like that. Okay, and this is equation 7.2. So as what it says is that as your uh, it gives you what happens to the crack width with respect to bar spacing and with respect to clear cover. Now, uh, now these two have some common region. Now, just give me a second. Just a second. Okay, so so this is giving us this is giving us all the values for certain W and beta values. So when you limit your crack width to a value of 0.016 inch, when you take beta is 1.2, okay, beta is 1.2, and Fs is 40,000 psi, and bar size is number 8. So for these particular values, the two equations were plotted. Okay, what is the maximum bar spacing you can get for particular clear cover? So let's say you can see that if you increase your clear cover, then your bar spacing has to come down, because see what I said, if you have a bigger clear cover, your crack widths become bigger, right? To compensate for that, your bar should be spaced more closely. Okay, and on conversely, if your bars are spaced wide apart, you cannot put too much clear cover. So there is a balance between these two things in order to maintain your crack width to be below this value. Okay, so how does equation 7.1 look? It looks like that. That means uh, you have to stay out of this region. So let me just use a shade. So I have to, so 7.1 is saying that I have to stay in this region. That is my safe region. Okay. Uh, Oh, I'm sorry, I drew the reverse. Let me just erase it. So for 7.1, for given clear cover, your bar spacing should be within that value. So sorry, you should be within this. You cannot exceed that value. Okay, so that is your value for 7.1. And for 7.2, it's giving you that you have to be here, right? So as per the ACI code, we choose some compromise between these two. That is, we choose this straight line. So we say that in this area, we are good. Okay. So 7.2 is I'm sorry, 7.3 is the compromised one that is adopted by the ACI code. And it is based on both these research done by Jurjari Lutz as well as frauds. And so this is limiting your spacing based on the clear cover. So this is what you take according to um, ACI code. Okay, this is like a compromise between the two quantities that you get from research. Now this is for, as I said, 40,000 psi. Now FS. So if FS is smaller, like let's say you use Fy is 40 ksi, then your FS can be taken as 2/3 of Fy, which is 2/3 of 40 ksi, which is 26,667 psi, right? So for all of these values, you have your bar spacing versus clear cover. So whatever you provide, that number should be inside the area enclosed by the straight line. Okay, sorry, not outside, of course. Outside you violated the specification. So you have to stay inside. Okay. Okay. Now let's do a quick check for one particular problem. So you have a T girder in a high-rise building, and you have a service load moment, 8,630 inch kip, and you have a clear cover on the side and bottom is given as 2¼ inch. Fy is given as 60 ksi. We want to see if we have meet the crack control specification in the ACI code. So just to show you the ACI 318 criterion that we are seeing for crack width. I have to reopen it. So you can see here, so deformed bar or wires, your maximum spacing is lesser of these two. Whichever is smaller, you have to stay within that. Okay. That's what I showed here. So what are we? Let's calculate for our case. You have a service load moment of 8,630 inch kips. So for this service load moment, what is your Fs, the stress in uh, the stress in the tension steel? So let's calculate that. So for service load, you will have a cracked section, and uh, your moment value is right. You have your steel area ASFS times your lever arm. Your lever arm is D minus A by 2. This should give you your moment. Okay. So you can assume uh, you can assume that uh, your compression zone, compression region is in exactly in the flange. So that is, you can assume your A value to be 6 inches. So therefore D, which is 32 and a quarter, minus A by 2. So minus 3 inches. So that's your lever arm. So AS10 number 8. So I will provide you the rebar chart, but let me just open it. So I will provide you this as well. If you remember um, your rebars, you have number 8 cross-sectional area is 0.79. So uh, so AS, you have 10 number 8. So your AS is 10 times 0.79 square inch. So that is 7, of course. Uh, so 7.9 square inch times Fs, that is the steel stress in serviceability loads. So D is 32 and 1/4, so 32.25 minus A over 2 is 3. This is inches. This is 8,630 inch kips. So from here you can calculate Fs is 8,630 divided by 7.9 times 29.25 KSI. So that is 37.35 KSI. So uh, so now let's go back and check our uh, criteria, lesser of 15,000, 15 times 40,000 by Fs minus 2.5 clear cover. So that is your first criterion. Second one is 12 times 40,000 by Fs. So the first one gives you a value of, so we use Fs is 37.35 KSI. So 15 times 40 over 37.35 minus 2.5 times clear cover. Clear cover is 2 and 1/4 inch. And this one gives you 12 times 40 KSI. So 12.85. The first one comes out to 10.44. So your lesser of the two is, so your maximum spacing as per the ACI 318 is 10.44. So let's follow one thing, that whenever you use any of the ACI 318 code, you must give the clause number 24.3.2. So you write here actually it should be here. Okay. So let's check what is this provided spacing. Is it within 10.4 inches? So as provided, how do you calculate? You have total width of 27 inch. Then you take out end to center is 2 and 1/4 plus half of bar diameter. Number 8 bar is 1 inch diameter, so half inch. Half plus 2.2 and 1/4 is 2 and 3/4. So you take out 2 times 2 and 3/4 on either side, and whatever is remaining, you divide that by 4. Okay, you have 4 spacings, so that is 5.375. Okay, so this is less than max, so it is okay. Okay, now okay, next is calculation of deflections. So here, since we will also, unlike in the undergraduate course where we only saw the simply supported case or cantilever, we will also look at indeterminate cases here. So we will quickly go over what are the best methods for deflection calculation. Okay. So before we go there, let's see first how we need to calculate the deflections. So the concept here is very important to understand. So let's go over that first. Okay, we will use this diagram to illustrate our concept. Let's make a new one. Okay. So okay. So before we go into the, okay, let's first see the basic formula. So general form for elastic deflection is delta is something over EI. So if you remember, for simply supported case, what was your deflection? 5 times WL power 4 by 384 EI. Do you remember this? Okay, let me just make a new slide. Uh, have it somewhere. Okay, I have it here. Okay. So anyway, I'll just explain. So you remember that your moment is E times I times phi, curvature, right? And your curvature is approximately a second derivative of displacement. So you have m by EI equals so when, depending on what moment you have, what are your boundary conditions, etc., etc., when you integrate it, then in the numerator you will get what you need to get. Moment is some load times L, a length factor, right? Then if you integrate it once, you will get WL square something. Sorry, moment already has a W and a L square term. W is the um, load intensity, right? For example, in simply supported beam, your maximum bending moment which occurs at the mid-span is WL square by 8. So your moment will have a W and L square term. Then you integrate twice, you will end up with another L square term, and then you will have some factor. Okay, we can put it in the numerator. You can put it in the numerator. You will have some factor, some number here, and then you will have a EI here, okay? So your deflection or maximum deflection will have a load intensity, that is load per unit length, and a length to the power 4 term and a EI term, okay? If you have a concentrated load instead of distributed load, you will have here a L power 3 term, and then you will have some number, and at the bottom an EI. Okay. So what does your deflection depend on? Of course, it depends on the load. So all this is for elastic deflection. Okay. So all this is for elastic deflection. Now, it depends on the load. It, of course, depends on the span of the beam. So if you have a longer span, you will have more deflection, right? And it depends on your moment of inertia. So this you know from your mechanics of materials. Higher the moment of inertia, the stiffer it is, the smaller is your deflection, right? Now, how do you calculate deflections in this reinforced concrete beam? Okay, so first thing is that it depends on the moment. Okay, how does it depend on moment? Now we said that at service load, so this is your beam. Let's say this is your reinforcement bar, and your beam has hairline cracks. Something like that, okay? Okay, so so you can see in between these two cracks, your beam is uncracked, right? That means in this region, in the region between two cracks, your beam is not cracked. So some places of the region you have a cracked beam, some places you have uncracked section. So your section is not constant, and moreover your moment is not the same uniform throughout. It will vary according to your moment diagram, right? So actually your computation of deflections is quite complex problem, because you don't have you have variable moment, and at every place there your beam is sometimes cracked, sometimes uncracked. So how do you calculate your deflection? So the code provides us a simpler method, that is using an effective moment of inertia. Okay. So effective moment of inertia is some kind of an average between your cracked section and uncracked section. Depending on how much is your applied moment, you will you will see where is your applied moment. Okay, let's say MA is your applied moment. Now MCR is your cracking moment, and that means where it just cracks, and okay, MA is your applied moment, MCR is your cracking moment. So you can see that if you have not cracked, then you can use the what moment of inertia you can use? I uncracked transformed. So if you remember what is uncracked transformed, so you have your beam and you have your reinforcing steel here. It has not cracked, right? So what will you do? You will convert the steel to equivalent concrete, right? So you will add some concrete here, and the area of that concrete will be n-1 area of steel. Remember modular ratio, equivalent beam, all of that from mechanics of materials. So according to that, you will calculate a I uncracked transform. This is what we will use if applied moment is less than cracking moment. Now, if your applied moment is more than cracking moment, then you are already cracked. So then you need to use the cracked moment of inertia, ICR. That is when MA greater than MCR. Okay, give me 1 second. Okay. Okay, so if it is more than MCR, you will use I cracked. If it is less than MCR, you will use I uncracked transformed, right? But it is not so simple as we said, because somewhere it is cracked, somewhere it is uncracked. So we will use a I effective, which is somewhere in between I uncracked transformed to I cracked, okay, which is some kind of average, interpolated value. So if your applied moment is quite small, okay, then you will get I effective to be very close to I uncracked transformed. And if your applied moment is very large, then it's almost cracked everywhere, then you will get it very close to I cracked, okay. The exact interpolation is from the code. Let's go there. So again, please note here is your, if your service moment, applied moment is less than or equal to 2/3 of cracking moment, then you can use the, okay, there is another thing here. Your ACI code specifies that you don't need to calculate uncracked transformed moment of inertia. You can ignore this small contribution from the steel. Just use the gross section. Just use the gross section to calculate IG. You can take IUT to be approximately IG. So that's what the code is allowing us to do. Now, so you see the interpolation. If applied moment is more than 2/3 of cracking moment, it is you do the averaging like this. ICR divided by 1 minus 2/3 MCR by MA the whole square times 1 minus ICR by IG. It looks somewhat complicated, but it is just a nonlinear interpolation between I cracked and between I gross and I cracked. Okay, depending on where your moment is, you will take somewhere in between as the effective moment of inertia. Okay, hope that is clear. Now, what did we say? We need the deflections depend on your load, they depend on the span of your beam, and they depend on the moment of inertia. Now, span of the beam is not changing once you built your structure. So we need to worry about load and, okay, elastic modulus is for all the concretes you can take, or for concrete, your material is not changing once you build it. So EC is 57,000 square root FC prime according to ACI code. If you don't remember, then it is in your 318 code. Just a second. Okay, sometimes I forgot the clause number, but okay. So 19, okay. So it is in chapter 19. Yes, here. Okay, that's right. So this is for normal weight concrete. For lightweight concrete, that is your formula. So that is fixed. What I'm saying is that the E value is fixed. So what is changing with your loads are changing, because when you're constructing the structure, you only have dead load, right? And then your live load is coming in and things are changing. So what is changing is your load and moments of inertia, because depending on your load, your beams will crack more or crack less. So moment of inertia, remember, I effective depends on how much it has cracked. So I is changing and load is changing. So we have to track both of these to understand the deflection. So let's first look at elastic deflection using this graph. Okay. Now, what I will explain now is the most typical case. Okay. Typical case. What happens in most of the cases. Okay. So here is your structure. And the structure is being built. Okay. So by the time it is built, already all the dead load is there, right? Because dead load is just self-weight of the structure, then the cladding, then the plumbing, and so on and so forth. So by the time your structure is ready, this is your dead loads are already all acting. Now, once it is ready, your live loads will come in, like maybe machinery, maybe people, maybe traffic, whatever, right? Okay, so what we need to do is, uh, let's say you have, usually this is the case, you have some machinery or some equipment that is going to come. So with that equipment, there will be over and above whatever deflection was already here. When this equipment came, the deflection due to dead load. Okay, let's put this notation first. It will be make it easier. So let's put delta delta D. Okay, E, or let's put delta DI. So we will use this notation. When we put delta, delta means deflection. When we put D here, it means dead load. I means instantaneous deflection. Okay. Okay. So when we put delta D, L means long-term deflection. Now, if I write delta Li, it means instantaneous deflection due to live load. Okay. So, okay, live load should be, before we write about live load, we note one thing, that live load will be broken into two parts. So I will write SLI USLI. So let's just understand what are all these notations. So the first one is dead load or live load, or what is SL? SL is sustained part of live load. USL is unsustained part of live load. Now, what it means? Sustained part of live load means, supposing you have some machinery that is coming in after the structure was built, right? That machinery is going to stay throughout the life of that structure now. So technically it is a live load, but just a second. Uh, Okay, so let's continue here. Now, okay, D is dead load. Okay, D is dead load. We, like I was saying, we split a live load into two parts, sustained part and unsustained part. So if it's like the machinery that comes in where as soon as the structure is built and it stays throughout the life of that structure, that is considered as sustained part of live load. And if it is a temporary load which is not going to stay for very long, it is counted as unsustained part of the live load. Okay. So why do we divide into two parts? It's because your dead load will be responsible for instantaneous or immediate deflections and long-term deflections. So the long-term deflections come because of creep, and instantaneous deflections are because of elastic deflection. So dead load will cause instantaneous deflection as well as long-term deflection or creep deflection. Now, that's the second subscript. I means instantaneous deflection, L means long-term deflection due to creep. Now, the sustained live load will cause both because it is there for a long period of time. It will cause instantaneous deflection as well as long-term deflection and long-term deflection. Now, unsustained part of the live load is going to not stay for very long. So it will only cause instantaneous deflection. Okay, so we understand how the different types of load will cause different types of deflection. Okay, this is going to influence how we calculate our total deflection and which total deflection is important. So in the typical case, your equipment is coming in or machinery is coming in. Excuse me. Your machinery is coming in immediately after the structure was built. Okay. So the instantaneous deflection due to dead load is not important for us because this is your structure. Okay. So let's say I draw it here. That's your structure. Now your beam, after the application of dead load, that is after everything was built, it already underwent the instantaneous deflection due to dead load. This thing has already happened. And after that happened, your equipment came in. So once that equipment came in, there will be more deflection. That is what is important for your equipment. So in the presence of your equipment, there was some additional deflection that will determine after you place your equipment what is happening. Okay, when it first comes in, that doesn't matter. So what happens after that, that will determine whether, okay, your deflection is within the tolerance or not. So what is that additional deflection? Okay, that has a few parts. What parts? First is delta DL, long-term deflection due to dead load. You need to count that. Okay. Then long-term deflection due to sustained part of live load. Instantaneous deflection due to sustained part of live load plus instantaneous deflection due to unsustained part of the live load. Now these two we can usually combine it as deflection Live load, instantaneous. Instantaneous deflection due to live load. And how is this calculated? This is calculated as in a very specific way. This is for the typical case, okay? We need to go case by case. For the typical case, instantaneous deflection due to live load is calculated as instantaneous deflection due to dead plus live minus instantaneous deflection due to dead load. So why do we need to calculate like this? Let me explain. To understand that, we need to look at the graph of moment versus deflection that you see here. Moment versus deflection. Okay. Now we are first at the stage where the structure is ready. It is built, but there is no live load that came in. Then what will be the loading path? Loading path is along here. So you load it all along here, and then here it cracks, right? So here at beyond this point, it is cracking. So beyond up to this point, your moment of inertia was constant, right? Moment of inertia up to this point was constant. What is that? I uncracked transform, which you can approximate as I gross, okay? Up to this point, up to the cracking point, that was the moment of inertia. So what is the relationship between M and I? M equal to, I'm sorry, between M and deflection. So you will have M times some length term square divided by EI and some number. Okay, this is your deflection. So that means your, or in other words, your slope, or this is y, this is M is on the y-axis, delta is on x-axis. M is equal to E times I by some L square, some number, times delta, right? So you have, if your I is constant, the slope of this diagram is constant. That means it is a straight line. So up to the cracking point, it's a straight line. After cracking, you need to use effective moment of inertia. Remember, effective moment of inertia depends on where, how much is your cracking moment. Remember the interpolation formula. Let's come back to chapter 24. Excuse me. Okay, so from the interpolation formula, you can see that effective moment of inertia depends on your applied moment. That means the more is your applied moment, the more it's going towards a cracked section, and your moment of inertia keeps going down. So that's why you see that beyond this point, your curve is not linear anymore. So here, from here up to the end, it's not, okay, from here onwards, you can, it is changing, it's still changing. And from here, this whole thing is the nonlinear part, okay? From here onwards, it's all nonlinear. Only up to the cracking point, it is linear, okay? So in the first case, let's say that your dead load generated somewhere here. Your dead load caused a moment that is somewhere here. This is the moment caused by just dead load. Everything is built, structure is ready, but nothing has come in. Then you're here. So that means you're on this point on the M delta diagram. So you have loaded it following this path. You have loaded it following that path, the green path. Okay. Now you are adding the dead load, right? You are adding the you are adding the live load. So let's say with the live load, your moment is here. Okay, that's the yellow one is the moment with the live load. That means here is D plus L, and the green one is just D. Now for D plus L, you are at this point. Okay. So what we are, like I said before, what we are interested in a lot of the times is what is the additional deflection cost after the load comes in. So that means we are interested in from this point to this point, because of placing that live load, how much was the additional deflection? Okay, this is what is delta D plus. So this deflection is delta D I. This deflection is delta D plus L I. So this difference is what we are interested in. Okay, for whatever comes into the build structure after everything is ready, those deflections are the ones that matter most of the time, but we will see that need not always be the case. So for those cases, this is how you will calculate your live load. And what is the total deflection that matters? To this, you need to add long-term deflection due to dead load, long-term deflection due to sustained part of live load. So whatever equipment or whatever you are placing there, it's going to see all of these things, this, and this. Of course, it will not see the delta DI because that already happened when it came in. Okay, hope all of this is clear. And we are going to, of course, apply this in solving problems. Now let's see another case where we have a slightly different scenario. Now what is the case? Now we say that this is your structure. But let's say during the construction of that structure, as it happens a lot of times, for many like bridges, precast bridges, precast pipes, and so on, what happens is during the construction of that structure, there was some construction equipment or something there, and so this construction equipment was much heavier than anything that is going to come later. Okay, that means after this is gone and the structure is ready, whatever live load and whatever comes in is all lighter than whatever this structure has already seen. Okay, okay, then you can see it gets a bit more complicated. Now, when the structure was ready, already this construction equipment was there. That means during the construction, during the load history of this structure, at some point of time, it already went to some faraway place and then came back. Okay, let me draw it again. Let's say that which point is dead load instantaneous deflection. Suppose this point is the instantaneous deflection due to dead load. But in this particular case, we cannot approach this point along this loading path. We cannot go along this loading path because the structure already experienced, it already at some point of time when the heavy equipment came in, it already went to some faraway point, let's say there. Or that's a bit too far. Let's say it went somewhere there already. Okay. And then it came back. That means next time you load it, it's not going to go that way anymore. It's going to go along this red path. Okay. So from this point on, whatever loads come in, they are not going to be higher than this. So everything that happens from this point on will all happen along this line, up and down this line. So when you apply the dead load, okay, in the previous case, this was your moment at dead load. In the previous case, this was your instantaneous deflection due to dead load, right? Di. This was delta di. But now this was in the previous case. Now your everything is happening along the green line. So that is going to be your delta di. And let's say your live load is somewhere here. That's your delta d plus, that's your moment at d plus L, suppose d plus L here. Then that's at this point. So now this will be delta d plus Li. So in this case, your delta L instantaneous is actually smaller than this case. Did you see? Because in this case, your heavy construction equipment and everything already cracked the structure as much as it's going to crack. So after whatever your load comes in, your instantaneous deflection due to live load is not going to be as high as in the previous case. So you can see here that this part, the instantaneous load due to the instantaneous deflection due to dead load, is a function of the loading history. So you have to be careful about what loads did the structure see in its history, and we have to calculate the deflections according to that. Okay, so as you might have noticed, as we were going through this, it is not possible to, for any structure, it's not possible to exactly know the loading history. That is, what load it saw at every point of time. It's not possible to know it in that detail. So there is quite a bit of tolerance which is acceptable in the calculation of deflection. So you're okay within about half, 1/4 to half inch even, or even a bit beyond that is okay. Where we don't want to, where we want a clear idea is where we are in the ballpark, okay? Whether we are in the ballpark. If we say that the deflection is 1 inch from our calculation, and the actual deflection is 1.25 inch, that's fine, we are okay. But if we say that our deflection is half an inch and the actual deflection is 2 inches, that's not okay. Okay, so we have some tolerance, but we want to be somewhere in the ballpark. So that's about our deflection calculation. Now, as I mentioned earlier, in the undergraduate course, we see mostly determinate structures, so we are not that worried about deflection calculation. We use most of these standard formulae that you see in this table. So simply supported, propped cantilever, and so on. So whatever deflections you see, whatever deflections you see in this table is what we use for simpler cases. But in this course, we will be dealing a lot with cases like continuous beams or other boundary conditions. So we need to go over some methods for deflection calculation. And let's just quickly go over that. Maybe only the most common ones we will be using. We will use these a lot. Virtual work method, moment area method, both theorem 1 and theorem 2, and direct integration method. Okay, we will use both of those. So let's first see direct integration. So this is only for the how to get that formula F by EI. This is your deflection calculation, right? And F is 5 by 384 as an example, WL power 4. This is for simply supported, uniformly loaded beam. Right? Sorry. Now we may not have uniform loading. We may have any kind of loading, any kind of supports. So let's just see let's just learn these theorems. First is direct integration. For this, we just go from the formula. M is EI d square y, or M over EI is d square y by dx square. So you integrate this. You integrate this first, you will get dy by dx is integral of m by ei dx plus some constant. This is over the length of the beam. Now you integrate again. Some constant, right? Now this is why you can apply your end conditions and get your delta at any point. So this is by direct integration. Then virtual work method. So what is a virtual work method? So you have, let's say you have your beam, and whatever type of loading you may have on the beam, something, let's say simply supported or whatever. So this is your real moment diagram. Let's say your real moment diagram is something like that, okay? So your real moment diagram divided by EI, this will be your curvature diagram. Now, let's say I want deflection at some point, at that point. Then what we will do is we will apply a virtual load, which is load of 1 at that point. And then this is your small m. This is the moment diagram due to virtual load, okay? This is the moment diagram due to virtual load. Now, how do you get your deflection? So you will say external virtual work is what? External load 1 times whatever deflection. That means you're making it go from the original configuration to the final configuration, but none of the real loads. You only have a virtual load. That virtual load is the one which is going with the beam from the original configuration to the final configuration. So this is delta at that point. So your external virtual work is 1 times delta. What is your internal virtual work? It's the energy. So energy is moment times d theta, right? Moment times uh, change in angle, bending. That is your work done by moment, right? Force times displacement, moment times rotation. That's work. So what is d theta? D theta is nothing but d theta is nothing but your what is phi? Phi is d theta by dx, right? Your curvature is what? If you have a very sharp change in angle within a very small distance, then you have a high curvature. So curvature is rate of change of the angle, right? So your d theta is nothing but phi times dx. So your internal virtual work is integral m d theta along the length of the beam, which is integral m times phi dx. But your curvature is nothing but obtained from your real bending moment. So m times m by ei dx. That is delta. Okay. This is your virtual work method. And let's see moment area method. This is also very useful. Theorem 1. Let's say you have any beam and you know its bending moment diagram. I'm just drawing a very rough bending moment diagram, something. Now, let's say that I want to know from this point to this point, what is the change in angle, okay? Just now we said curvature is nothing but, so this is point A, this is point B. I want to know what is the change in angle. That is, if I draw a tangent at point A, another tangent at point B, then what is the difference in their slopes, okay? So we said already that d theta by dx is the curvature. So which means d theta by dx is m by ei. So d theta. So if I want theta b minus theta a, this is integral of m by ei dx from a to b. That is nothing but area under the curvature diagram is giving you change in angle between 2 points A and B. Just a second. Okay. Uh, okay, sorry. Okay. Now, all right. Uh, what is theorem 2 of moment area method? Okay, sorry, just a second. Okay. Theorem 2. So we have a beam. We know the moment diagram, something, let's say like that. Now, we take 2 points, say this point and this is point A, this is point B. Now, what this theorem is telling us is if I draw a tangent at A, how far is this from B? Okay. How far is this tangent from B? This we call as delta, sorry, not delta, we call as T A comma B or T A by B. So T A by B, how do we get this? Now, imagine that for any point in between, this is one tangent, this is the very next tangent. What is this distance, this small distance? Now you went through dx, right? So whatever is this change in angle, that times dx, because beam deflections are all very small, so this thing is all very flat almost. So if from here to here, if you have a dx distance, then what is the change in angle between them? Change in angle is phi dx, right? That is your change in angle, d theta, between them. Now, that d theta is this angle. Let me blow up this figure. It will look something like that. This angle is d theta, and this this length is d theta times this is dx. Now, as I said, this d theta is not so inclined. All of them are almost very flat. Okay. Okay. So this distance. Now, phi times, I'm sorry, not this is not dx, this is dx, so this is x. Phi times, this is x, right? So your phi dx times x, that is the dt. So your TAB, shift, your TAB equals integral of dt from a to b, which is integral of phi dx times x from a to b, which is integral of phi is what? M over ei x dx from A to B. What it means is if you take the moment diagram, divide by EI and make it into the curvature diagram, then this distance TAB is nothing but the moment of this area between A and B, and moment, that means you will take the centroid of this area, wherever it may be there, centroid of this area times this distance x bar, okay? So this will be equal to your area under the moment diagram, area under curvature diagram times x bar. X bar is the distance from centroid of this area to B. That area times x bar is TAB, okay? So this TAB will be very useful in calculating deflections. Right now, it may not seem immediately apparent, but let me give you an easy example. Now, let's take simply supported beam, right? How does it bend? Like that, right? Where is the maximum deflection? At the center, right? Okay. Now, how to use the theorem? You draw tangent here, draw tangent here. What is the distance between this point to tangent? That's the deflection that you need. So if you take this point as A, this point as B, then your answer is just TAB directly. So that means for simply supported beam, if you take this area and multiply by this centroid, that is 2/3 of the distance x for parabola, you directly got your answer. So a lot of times moment area method will give you your deflection in a very short shortcut. Okay, so we stop here for today, and we will again, like we decided, we are going to start again Wednesday 7 a.m. Now, one thing I forgot to mention, the syllabus I'm going to post, but we will have one thing that is not in the syllabus. Recently, I went to professional development seminar, and we will be having in one class, one of the classes. Let me stop the screen share. We will have Mr. Al Hogan. He has more than 50 years or 40 years experience in concrete pipes. So he will be teaching hydraulic design and structural design of concrete pipe, okay? That may be in the later part of the semester, maybe sometime in November, but he will do it in person. So for that particular class, please, you need to come in person. If you want, we can fix the evening time just for that one class. But however it is, we need to arrange so that everything is in person, okay? Okay, thank you. We will see you next class.